Alright, we're getting started with the Chapter 8 Homework B review. This is the second of two assignments on this chapter, which deals with gases. And after this, we'll just move into our last two assignments, which are on Chapter 9. So this week's assignment dealt with basically two major topics. So the first of those was primarily numerical type problems dealing with mixtures of gases, where the key concept there is Dalton's law of partial pressures. The idea that when you mix two or more gases together, the pressures are additive, and that's dependent on the amount of each gas you have in terms of moles, in terms of how much each gas contributes to that pressure. So we'll give a few problems like that, and then the rest is more conceptual, primarily dealing with kinetic molecular theory, the idea that gas molecules are constantly moving around and how that affects the pressure and things like that. So there's going to be some concepts as well that we'll go over in this review. The average this week was 9.56 out of 12, basically identical as the last time we gave this assignment, so nothing to really concern ourselves there in terms of the score. So let's get right into it. And so the first few we're going to deal with are talking about mixtures of gases. So this first one here, we have 0.75 liters of argon at 1.5 atmospheres, 177 degrees Celsius. That's gas 1, or gas A if you want to call it that. And then for the second one, we have 0.235 liters of sulfur dioxide, and it's at a different pressure, 95 kPa and 63 Celsius. They're added to a 1 liter flask, and the temperature is adjusted to 25 degrees Celsius. What is the resulting pressure of the flask in atmospheres? So what we're basically doing here is we're combining two gases. So each gas initially has its own temperature, pressure, and volume. And then we're mixing those two together into a 1 liter flask and lowering the temperature down to room temperature. So initially they were at 177 Celsius and 63 Celsius. Once we mix them together, we lower the temperature. So in a problem like this, what you're basically going to do is you're going to, and this was our second gas, gas B, what you're basically going to do is for each gas A and B, whatever they are, the identities of the gas don't particularly matter because we're all dealing with the ideal gas equation, which doesn't care what gas it is. But for each gas in the mixture, you're going to use the ideal gas law to figure out what is going to be the pressure of that gas under the new conditions. So if you look at the two gases, gas A, which is argon in this case, the initial volume is 0.75 liters. The initial pressure is 1.50 atmospheres, and the initial temperature is 177 degrees Celsius. And then for the second gas, gas B, it has separate initial conditions. And then the initial pressure for that one is 95 kPa. We'll put that into atmospheres because our final answer is going to be in atmospheres anyway. So we'll divide that by 101.3 to get atmospheres, which is 0.938. And the initial temperature for gas B was 63 Celsius. So then what we're going to do is that's going to be the initial volume, pressure, and temperature for each gas. And then for both gases, for the mixture, once you mix them together, they're all going to be at the same volume. So they're all going to be at 1 liter once we mix them together. And they're both going to be at the same final temperature, which is 25 degrees Celsius. And so then what we need to figure out is for each gas, what's the final pressure P2? Organize this in a different way. And so for this mixture, the total pressure is going to be the pressure of gas A plus the pressure of gas B after we mix them together under these new conditions. So for each gas, we're going to basically do an ideal gas law problem, where the number of moles in R are constant, and we're going to just set it up as P1 PV over T is constant for each gas, and then P1 V1 over T1 equals P2 V2 over T2. And we're going to do this for both gases. So it's a lot like the problems we did last week, but now we have to do it for two different gases. And so for each of those two gases, we're going to solve for P2, the final pressure under the new conditions. And then to get the total pressure, we have to add together P2 for both gases A and B. All right, so it's a few steps here, three basic steps. We're going to do this twice for each gas, once for each gas, and then we're going to add the two at the end. So for gas A, then its pressure, and to keep these straight from each other, I'll call this. Just call it P2 for now. But anyway, for gas A, P2 is, for both gases really, P1, B1, T2 over B2, T1. And so we're going to do that for gas A. So for gas A, again, we have the initial conditions written up there. So it's going to be 1.50 atmospheres for P1, 0.75 liters for B1, and then T2 is the final temperature after mixing, which is 25 Celsius. So those are going to be the same for both gases after they're mixed. And then in the bottom, V2 is the final volume, which is 1 liter. And then T1 is the initial temperature of gas A, which is 177. So we need to convert that to Kelvin, so that's going to be 450. So for gas A, the final pressure, the final partial pressure in the mixture I got 0.745 atmospheres. So it increases volume and it increases temperature, so its final pressure is lower than it would initially started at. And then for gas B, we do the same thing. We calculate its P2, call this P2A and P2B to keep them straight from each other. I'm going to keep the same notation. I'm all over the place in this problem with notation. But basically what we're going to do is we're going to find P2 for both gases A and B and then add them together to get the total pressure. So let's call that P2A and P2B just so we keep them straight. So for gas B, we're going to use, again, it's still going to be P1, V1, T2 over B2, T1, but the initial conditions, P1, V1, and T1 are different for gas B, so we put those numbers in. So for gas B, its initial pressure was 0.938 atmospheres. The initial volume for gas B was 0.235 liters. And then it's going to have the same temperature and volume once they're mixed together. So T2 for gas B is still 25 Celsius for 298 Kelvin. And then V2 is still 1 liter for gas B. Once they're mixed together, they're going to occupy the same volume. But then T1 for gas B was 63 Celsius. Plus 273 is 336. Alright, and so then we're going to mix those two together, multiply that out and then add them together. So for gas B, the final pressure after mixing is 0.195 atmospheres. So that's the pressure of each gas individually after mixing, and then the total pressure is going to be, again, the sum of those two. So it's going to be 0.745 atmospheres, which is the partial pressure for gas A after mixing, plus 0.195 atmospheres, which is the partial pressure for gas B. And that comes out to 0.940 atmospheres. Alright, so assuming I didn't mess up any of the math, that's how that one would go. You're going to do an ideal gas law problem for each gas in the mixture to find out the partial pressure after mixing. That's those two numbers there, and then add them together. So it's a few steps, but none of them are terribly difficult. The first two steps are just what we did last week on the homework assignment. And then we have to add them together because they're mixed, so the total pressure is going to be the sum of the two. Now, another context where we commonly saw the idea of Dalton's law and mixtures of gases was in these problems where we're collecting a gas over water. So again, when you describe the experiment in class, you run a reaction, you generate a gas, often hydrogen, but not always, and then that gas is going to bubble through water and be collected above the water, and you measure the volume change of the liquid level to tell you how much gas was collected. But when you do that, above the surface of your liquid, you have a mixture of the gas that you're measuring and water vapor, some small amount of water molecules that are in the gas phase at whatever temperature you're at. So this is a very typical problem like this. So we have 957 milliliters of hydrogen, that's the volume of the gas. It was collected over water at 25 Celsius and a pressure of 765 torr. Now what's important to recognize is that 765 torr is the total pressure of the mixture. And again, in these types of problems, the mixture of gases that we're considering is the gas we're collecting, which is hydrogen, and then water vapor pressure. Okay, so we have those two things that we have to consider when we have a mixture of gases. Okay, so then what we'll do is, for this type of problem here, we have to subtract the two pressures to figure out just what the pressure of hydrogen is. Because in problems like this, what you're normally going to do is we're using PV equals nRT eventually for hydrogen. But if we want to find the number of moles of hydrogen, we're going to solve this equation for number of moles. It's going to be the pressure of just the hydrogen gas times volume over RT. So we have to find the partial pressure of hydrogen to figure out what portion of that gas is made up of that gas, hydrogen. Alright, so anyway, what we're going to do is we're going to subtract the two. So the pressure for H2 is going to be the total pressure minus the water vapor pressure. And so our total pressure is 765 torr. Water vapor pressure at that temperature is 24 torr. And so subtracting those two, we get 741, and that's going to be the pressure of hydrogen. So if you don't do this step of subtracting out the water vapor pressure, you're going to get an answer that's a little bit too big, and it will be outside of the range of answers that we would accept on a problem like this. And then we're going to want to put it back into the atmosphere, because now we're going to use the ideal gas equation. So let's put it back into the atmosphere, 0.975. Alright, and then so what we'll do is we'll solve for number of moles of hydrogen using that as the partial pressure of hydrogen. So the partial pressure of hydrogen we found out was 0.975 atmospheres. We have to use atmospheres here because we're using R in this calculation. The volume of gas that we collected was 957 milliliters. That needs to be in liters for ideal gas equation. So unit conversions are fairly important in problems like this. And then RT is 0.0821 liter atmospheres per K mole. And then the temperature was 25 degrees Celsius for both gases, the whole thing, so it's going to be 298 Kelvin. So that'll give us the number of moles of hydrogen. So I got 0.0381 moles. This is asking for the mass of hydrogen and gas. Now, if you remember, the formula wasn't given here, but hydrogen gas, the standard state for hydrogen is not HH, it's H2. So if we want to find the grams of hydrogen, we have to remember that the formula is H2. So we're going to take the number of moles, which is 0.0381 that we just found, and we're going to multiply that by the molar mass of H2, which is 2.02, 2 times the atomic mass of hydrogen. Alright, so another possible mistake in this problem was forgetting that hydrogen is actually H2, not just H. So we're going to multiply that by 2.02 grams per mole, and we should get a mass that's 0.0770. So if you had this problem and you want to sort of figure out, if you didn't get it right, why did I miss it? Again, the two most common mistakes are going to be either forgetting to subtract out the vapor pressure of vapor pressure of water from the total pressure, in which case you would get a number that's too big, or if you had just used H instead of H2 for hydrogen gas, if you used the wrong atomic or molar mass, then you would have to have a number that's smaller. So look at what you got for this, and you can try to maybe figure out where your mistake might have been. But this is a very standard problem type that we saw a few times in this assignment, and is likely to come up in future exams as well. Alright, another question that deals with mixtures of gases. So here we're trying to find something about the mass of a gas. So we have a mixture of oxygen gas. Again, we have to make sure we get the formulas for these right. So oxygen gas is O2, nitrogen gas is N2, and then carbon dioxide is CO2. So if those three gases mixed together, that's basically mostly what's in air. And we have a 10-liter container at 25 degrees Celsius with a total pressure of 12.5 atmospheres. If there are 30 grams each of oxygen and nitrogen, how many grams of carbon dioxide are present? So in problems like this, when we have the total pressure of the mixture, typically the first thing we're going to do is we're going to find out the total number of moles. Because if we start with PV equals nRT, the total number of moles of gas that we have in the mixture is going to be equal to the total pressure times volume over RT. Alright, so in this case we need to find total number of moles that we can subtract out the moles of oxygen and nitrogen and then figure out how much is left for carbon dioxide. So we're going to find total number of moles using this equation. So we have 12.5 atmospheres as the total pressure. The volume of the gas is 10 liters. And then we're going to use R, which is the universal gas constant. And the temperature is 25 Celsius again, or 298 Kelvin, basically, in temperature, which is why that temperature is so common. Alright, and then so we multiply this out. What I got was, let's see, that's right, 5.11 moles. Now this 5.11 moles, this is going to be the moles of all three added together. So the moles of oxygen plus the moles of nitrogen plus the moles of carbon dioxide, those added together equal that number, 5.11. And then what we'll do from there is we know the masses of oxygen and nitrogen, so we'll figure out the moles of each of those. So the moles of O2, we have 30 grams of it. So we divide by the molar mass for O2, which is 32. And so we have, we'll leave some extra digits here just so we don't round too much, 0.9375 moles of O2. And then the moles of nitrogen, we have 30 grams of that gas as well. And there's a couple of ways you can do problems like this in terms of either partial pressures or moles, but I think doing it in terms of moles is usually a little bit more straightforward. But you may have done this problem a slightly different way, and there's at least one other way to get to the answer. And then so for nitrogen, we get 1.071 moles of N2. So what that means is that the moles of CO2, we're just going to do that by difference. We're going to take the total number of moles, which is 5.11. We're going to subtract the moles of oxygen, 0.9375. And we're going to subtract the moles of nitrogen, which is 1.071. So what that leaves us with for CO2 is 3.155 moles. That's moles of CO2. And then finally what this is asking for is grams of CO2. So it's going to be that number times the molar mass of CO2, which is 44.02, carbon plus 2 oxygens. And so what I got was, didn't know how many depth places it wanted, but I got 130, we should probably do 3 simple figures, 139 grams of CO2 should be fine. Alright, and so that's what I got for grams of CO2 after we subtract out nitrogen and oxygen multiplied by molar mass. So let's double check if that's right. Yep, that should be about right. So again, maybe some rounding there, but the answer should be very close to that. So 139 grams of CO2. So again, in problems like this, a few steps involved, but we're going to start with PV equals nRT to find total number of moles, and then from there, it's just a sum of those. We know 2 of the 3, so we just have to do the other one by difference. Alright, and then the last problem I'll do on gas mixtures is this one here. So we have total pressure of 300 torr for a mixture of gas, and it contains equal masses of neon and argon. What is the partial pressure of neon and torr? Hint, what is the mole fraction of neon? Now we could do this algebraically because, you know, we know the mass of neon is X and the mass of argon is X, and so we could do a bunch of algebra to figure out, okay, if that's the mass of each gas, what's the relative number of moles and what's the mole fraction and so on. And that's the hint we're given, is what is the mole fraction of neon, because if we want the partial pressure of neon for this mixture, the mole fraction of neon multiplied by the total pressure is going to give us that. So this is another form of Dalton's law. In the previous two problems, we were just adding pressures together, which is always valid, but here, what's going to be more useful is to use mole fraction. So if you want to find the partial pressure of one gas in a mixture, you find its mole fraction, which is the moles of that gas over total moles multiplied by the total pressure. So that's what we're going to do here. Now we don't have real numbers though for masses, but they're equal, so we can just assume whatever we want. So we could do it sort of algebraically, just use a variable x for mass, or alternatively, let's just assume a mass, and let's look at a mass that's going to be convenient for us. So for neon, the atomic mass is around 20. So these are numbers from the periodic table. I'm not going to go back and forth the periodic table. But for argon, the atomic mass is around 40 from the periodic table, grams per mole if we put units on it. So what I'm going to do to make my life easy is I'm going to assume 40 grams of each gas. And so by doing that, we'll have exactly 1 mole of argon and 2 moles of neon. So if we assume 40 grams of each gas, again, you can assume whatever you want. The masses are equal, and we're not telling you anything about volume or temperature. We're just telling you about pressure. So you can assume whatever mass of a gas you want, and you'll still get the same answer. But if we assume 40, then the numbers are convenient. And so then that means the moles of neon in this mixture, we have 40 grams, and then the molar mass for neon is about 20. We're rounding a little bit here, but we're not going to be willing to be too exact for this. So we'll have 2 moles of neon, and then the moles for argon is going to be 40 grams of that also with an atomic mass of 40. So we have 1 mole of argon in that mixture. So then what we can do is we can easily find mole fraction of neon. Whatever masses you chose, or if you'd done it algebraically with just X, you would have gotten this as well. The mole fraction of neon is 2 moles, which is the moles of neon, divided by the sum of the two, which is 2 moles of neon plus 1 mole of argon. 2 over 3 is going to be the mole fraction of neon. And then we're going to use this equation here to find the partial pressure of neon. So the partial pressure of neon is the mole fraction, which is 2/3, times the total pressure, which is 300 torr, which comes out to 200 torr. Alright, so the partial pressure of a gas depends on the relative number of moles of that gas, not the mass. And so even though we have the same amount of each gas, 40 grams of each, the partial pressure for neon is twice as big, 200 torr. The rest of that, 100 torr, would be for argon. Alright, so that's going to be how we would approach that problem. It's a little bit abstract because we didn't give you anything except for the partial pressure, but we can assume whatever mass we want, and from there we can find mole fraction and we're off to the races. Alright, the next few problems are conceptual, so we're going to transition into the other major topic, which was kinetic molecular theory, the behavior of gas atoms and gas molecules at the molecular level, at the microscopic scale, and how that then relates to things like pressure and temperature and those things. So the first problem here deals with 2 different gases, hydrogen and oxygen, and they're both at the same pressure and temperature. And we want to know which statement accurately describes the gases, and the answer choices are in terms of kinetic energy and molecular speed. So the first thing we want to think about, let's think about kinetic energy, because 3 of the 4 answer choices deal with that. The average kinetic energy for a gas is equal to 3/2 RT. Now the important part, whether you remember that equation or not, we're not really going to use the equation directly, but the important point is that kinetic energy only depends on temperature. Average kinetic energy, I should say. Only depends on the temperature. Alright, so if you're comparing 2 different samples of gases, or more than 2 different samples of gases, to figure out which one has the highest average kinetic energy, you just have to look at the temperature. So in this case, both gases are at 25 degrees Celsius, so because they're at the same temperature, they should have the same average kinetic energy. All right. So anytime the gases are at the same temperature, their average kinetic energy will be the same. So if we look at answer choices A, B, and C, the average kinetic energy of the molecules should be the same, and so that's what choice C says. The average kinetic energy of O2 is equal to that of the H2 molecules. So that has to be true because the two gases are at the same temperature. In this problem, it's not possible to have more than one answer choice correct because there is no answer choice that's two of the above. So that means we can just stop there if we want to. Now let's make sure that we can verify that choice D is incorrect. So now we're talking about average molecular speed, and that's going to come up also in the next problem. We also have to realize that the average kinetic energy is equal to 1/2 mv squared, where v squared in this case with the bar above it is average velocity, or average speed. So if we're comparing the average speed of the molecules, that does depend on the mass. So for gas molecules that have the same kinetic energy like these ones do, if you have a smaller mass, you need to have a larger average velocity to make the kinetic energy the same. So if m goes down, v goes up, and vice versa. The gas that has a larger mass will have the smaller average velocity. So for gases at the same temperature, the lighter gases are going to be moving faster, heavier gases are going to be moving slower. And so for choice D here, the average molecular speed of molecules of O2 is greater than hydrogen. That one is the opposite of what should be true. That one is incorrect. Because oxygen is heavier than hydrogen, so at the same temperature with the same kinetic energy, the oxygen molecules will be moving slower, so their average molecular speed would be smaller than H2. So this one is incorrect also. So the only answer that is correct is choice C here, which deals with the kinetic energies of the gases being the same because their temperatures are the same. And then this problem here is really the same concept, but now again dealing with average molecular speed. So they're all at the same temperature, 25 degrees Celsius, so all have the same average kinetic energy in this case because they're all at the same temperature. But again, as we just said, the average kinetic energy is 1/2 mv squared. So if we're talking about average molecular speed, we need to account for the mass or the molar mass of each gas. So again, the lighter gases are going to have higher molecular speeds, and the heavier gases are going to have lower molecular speeds. So at the same temperature, if we're looking for the greatest average molecular speed, we need to find the gas that's the lightest. And of course, the lightest gas is going to be the one that has the smallest molar mass. So for N2, the molar mass is 28 grams per mole. For CH4, it's 16 grams per mole. Krypton, I don't remember off the top of my head, but that one's pretty heavy. Let's see what that is. That would be from the periodic table. And so the atomic mass for krypton, let's see, is 84, let's just round, 84 grams per mole. That one that says is pretty heavy. Helium is only going to be 4 grams per mole, and then CO2 is 44. So the one that's going to be moving the fastest is the lightest of these, which is helium. And that's going to be our answer then, choice D. Alright, so I need to pause for a quick second, but I'll just be back in a hot minute. Alright, resuming, and we're going to go on to the next one, which again is a conceptual question dealing with gas velocity and things like that. So if the volume and temperature of a sample of gas are increased at a constant pressure, so here we're not comparing two gases, we're just talking about a single gas where we're increasing the temperature and the volume, and the pressure is staying constant. The average molecular velocity increases or decreases, the average force of an individual collision decreases or increases, and the average number of collisions with the wall per second, do they increase or decrease? So there's a few different concepts going on here, but basically what's at the heart of this is that the pressure in a gas is proportional to the product of the frequency of the collisions and then the force of those collisions with the wall. So pressure is exerted because gas molecules collide with the wall, and that pressure is proportional to really the product of two things: how often the gas molecules are hitting the wall and how forceful those collisions are. So now we think about which parameters sort of influence these. So the force of collisions is determined exclusively by the temperature of the gas. In other words, how fast are the gas molecules moving? So if you raise the temperature of the gas, each average collision is going to have higher force or more force associated with it. So when we're talking about raising the temperature, so here we are increasing the temperature, so that means the force of the collisions should increase. So this one we know is going to be increases. Right, because anytime the gas molecules are moving faster, when they hit the wall, they're going to do that with more force. But then the one for frequency of collisions, this one depends on both the temperature and the volume. So for the frequency of those collisions, it's going to increase when the temperature goes up, but it's going to decrease when the volume goes up. So if we raise the temperature at a constant volume, the collisions will be more often because we're in the same volume, but the gas molecules are moving faster, so they're going to hit the wall on a more often basis. But then if we increase the volume at a constant temperature, we're making the volume larger, so the walls are farther away, and that means the gas molecules are going to hit them less often. So in this problem here, we have two competing things. We're increasing both the volume and the temperature. So by itself, increasing the volume would decrease those collisions. But then the increasing the temperature by itself would increase the frequency of collisions. So both of those are kind of working against each other. Now before we get to that, let's talk about the first part. I forgot to talk about the first part. So if we increase the temperature, as we talked about in the last two problems, the average molecular volume increases as well. So that's probably the most straightforward one, is this first one here. The molecular velocity increases with temperature because the kinetic energy increases, but all four of the answer choices have that, so we can't distinguish on those. So now we have to figure out what happens to these other two here. So we know that the force of collision, now let's talk about the average number of collisions with the wall per second. Well, we said the pressure is the product of these two. And we know unambiguously that the average force is increasing in this situation because we're raising the temperature, but the pressure is remaining constant. We're saying that we're doing this at a constant pressure. So in order for the pressure to stay constant, if the force of the collisions is increasing, that means the frequency of the collisions has to be decreasing. So even though, again, these increases in volume and temperature kind of work opposite in terms of their effect on the frequency, we know that we're keeping the pressure constant. So if the force of the collision is increasing, the frequency has to be decreasing. And so the average number of collisions with the wall per second, which is the frequency of collisions, has to decrease in this case. And the reason it has to decrease is because the pressure is staying constant. In order for that to be true, if one of them is going up, the force of collisions is going up, the other one, the frequency of collisions, has to go down. So it's going to be increases, increases, decreases, which should be choice B here. Okay? So the first two are unambiguous because the average molecular velocity has to increase when the temperature increases, and the average force has to increase when the temperature increases. The next one we had to, again, think about a little bit harder. Although the only answer choice that has even the first two correct, I guess A or B would work. So we have to distinguish that last one as well to narrow it down to choice B as the correct answer. All right, so that one, again, required a little bit of thought and reasoning, but it's really this key concept here. When you're thinking about the pressure of a gas, it's going to be dependent on those two things: how often the gas molecules hit the wall and how forceful those collisions are, and those two together give you the pressure. All right, the last two problems here are numerical problems dealing with molecular velocity, and the concept that's kind of most directly related to that is effusion or diffusion. Effusion being leaking, diffusion being a gas moving through space or moving through another gas. And those both are related to molecular velocity, but they have a simpler relationship because we're typically going to do this as sort of a relative sort of approach. So here we have an unknown gas Q requires 2.4 times as long to effuse under the same conditions as the same amount of nitrogen gas. I'm actually going to do these problems in the opposite order. They're really the same concept, but this one's a little bit more straightforward. So here we have an unknown gas Q that effuses 1.56 times as fast under the same conditions as xenon gas, what is the molar mass of Q. So in this problem here, we're talking about the rate of effusion. We're talking about how fast it effuses. So the ratio of the rates of unknown gas Q and the other gas which we're comparing it to is xenon. Those are going to be inversely related to the square roots of the molar masses. So we're talking about how fast a gas is effusing. It's inversely related to the molar mass. Lower molar mass means faster effusion. Higher molar mass means slower diffusion. And so that's going to be equal to this ratio here. Sorry, we have to flip the side of the equation, so I almost screwed that up myself. It's going to be xenon over Q. So if we're comparing the rates of Q to xenon, in terms of molar mass, they have to be flipped under the square root sign. So in this problem, the unknown gas effuses 1.56 times as fast. And so that means this ratio here is equal to 1.56, and that's going to be equal to the ratio of the square roots of the molar masses. So it's going to be the square root of the molar mass of xenon over the square root of the molar mass of Q, which is our unknown. So xenon is an element, so its molar mass is the atomic mass straight from the periodic table. And so xenon is an atomic mass of 131.3. So we're going to use that number here. And so this is the equation we have to solve for our unknown molar mass. So we're going to square both sides. So 1.56 squared is going to be equal to 131.3 divided by the molar mass of Q. And so when we solve for the molar mass of Q, just using that algebra, that will give us the answer there. So 131.3 divided by 1.56 squared should give us 53.95 is the molar mass of Q. Alright, and it should be smaller than xenon because we're telling you that the unknown gas effuses 1.56 times as fast. And so if it's effusing 1.56 times faster, then that means it has to be lighter in terms of its molar mass. And so we get a number that's smaller, and this is the math that we do to get that. So we're talking about rates of effusion. It's going to be an inverse relationship. Now the problem before that, which I meant to put in the opposite order, this one we're talking about how long it takes to effuse. So in this case, the gas Q requires 2.42 times as long to effuse. So here we're talking about the time that it takes to effuse. Time of our unknown Q divided by the time of the other gas, which in this case is nitrogen N2. Remember that nitrogen is N2 again. The ratio of the times that it takes is 2.42, and that's going to be directly related to the square roots of the molar masses. Because in this case, we're talking about how long it takes to effuse. The heavier gas is going to take longer. The lighter gas is going to be shorter because it's going faster. Anyway, those are directly related. So now we're going to put Q on the top and N2 on the bottom because that's the ratio we're considering in time. So you have to remember that there's two forms of this equation. And so we're going to put the molar mass of Q on top, that's our unknown, and then the molar mass of nitrogen on the bottom, which is 28.0 grams per mole, the molar mass for N2. So this is, again, pretty simple algebra. Now we're going to square both sides. And so the molar mass of Q over 28.0 grams per mole is equal to 2.42 squared, whatever that number is. And so then we just cross multiply to find the molar mass of Q, which in this case should be larger than nitrogen because if Q requires more time to effuse, that means it needs to be a heavier gas. And so when we multiply 28 times 2.42 squared, we get 164. I don't remember, didn't specify how many specific figures used, but it should be 3 based on the numbers in the problem, so we should get 164 grams per mole. So if it takes longer to effuse, that means it must be a heavier gas, and in this case the relationship between effusion times is going to be directly proportional to the square roots of the molar masses. So there's two different forms of the equation. Those two problems use them. This first one here that we did out of order was, again, the more standard form of the equation. The other one we had to flip one side to make them directly proportional. All right, the last question I'll go over is going to be deviations from the ideal gas law. So in reality, no gas is going to perfectly follow the ideal gas law, but under certain conditions they will follow it more closely than others. So what you really just need to remember is that to more closely follow the ideal gas law, here's the things you need to consider. So what you want for it to follow the ideal gas law, for the gas to behave ideally, is you need the molecules of gas that are present to not be interacting with each other at all. Because the reason that real gases deviate from ideal gas behavior to begin with is because the gas molecules are interacting with each other. They have intermolecular forces, as we're now talking about in Chapter 9. And so that's what causes those deviations. So if you want to avoid those deviations, here's a few things you want to consider. You need to have the molecules moving fast. If they're moving fast, they're not going to interact with each other as much because they're just zipping right by each other, not being in contact very much. So that means you need to have high temperature to avoid deviations from the ideal gas law. And then you also need the molecules spread far apart. Alright, because if the gas molecules are far apart from each other, again, that means they're not going to be in close contact, they're not going to have those intermolecular forces. And so that means some combination of low pressure or large volume will accomplish that. So those are the conditions under which you have the fewest deviations from the ideal gas law. When the temperature of the gas is high, meaning that the gas molecules are moving fast, or when they have low pressure and large volume, meaning that they're far apart from each other. So here the answers are in terms of temperature and pressure, and one in terms of volume as well. So for real gases, deviations from the ideal gas law are less, as we said, at high temperatures. That's going to be either A or B here, which is high temperatures, and then low pressure or large volume. So B has also low pressure as part of the answer. For choice E here, we have low temperature and high volume. So high volumes would give us small deviations, but low temperatures would not. So the one that's going to be the best choice is B here, because under both of those conditions, you have high temperature, so the gas molecules are moving fast, they won't interact with each other, and low pressure is meaning that they're far away from each other, so again, they're not forced to interact with each other. Okay, so those are the situations when you have the fewest deviations from the ideal gas law. And in terms of, when we talk about real gas behavior, those are the main things we expect you to know. We didn't go real deep onto that topic. We talked a little bit about the van der Waals equation, which are the corrections for the ideal gas law that you should at least know what they mean. You don't have to really use them numerically. But again, this concept here about when do they deviate less, that's an important one that will likely come up for you in future assessments. Alright, so that takes us to the end of this week's assignment. As usual, make sure you go through your results and that you know how to do every single question that you had on this assignment. And if there's anything that you're not sure about, please come and talk to me and we'll get that squared away. Alright, I'll see you guys in class this week, and we'll hopefully have a good last 2 weeks of our semester.